So if you were tired of hearing 2 hours of me earlier today, I apologize. You get a little bit more. And if you're feeling like it's been information overload, I'm going to apologize again because I'm going to overload you with even more information. What we actually want to do is provide another complementary piece of the puzzle here to complement what Martijn and David just presented to you. And just to recap kind of what you just heard from Martijn and David, one of the key themes that you should have seen and heard, and I chatted with a few folks at the break to discuss this a little briefly. What we've been observing, which is certainly not what we expected, is that different methods, when applied to different databases for different outcomes, exhibit different types of bias. So we can't, just as we're not recommending that there's a one-size-fits-all solution for which method to use, we can't tell you that there's a one-size-fits-all problem of confounding or a one-size-fits-all solution for how to deal with confounding. As Martijn showed you, there are certain designs, like the case control design, when applied to a particular database for renal failure, we observed that it was positively biased. And yet, when we applied temporal pattern discovery to the same exact database and the same exact outcome, it was negatively biased. Some databases were shifted one way or the other. Some databases had more variability than others, and similarly with different methods. And what David was basically showing you is, based on how much bias and how much variability you've got, how much can we learn in terms of estimating a posterior probability? So basically telling you what's the likelihood that you're looking at a true effect. So I'm going to shift gears and provide a slightly different spin on that, which is to provide another piece of potential learning that we believe we can extract from observational data. So one thing so Martijn was asking the question about how to do traditional null hypothesis testing and what is the correct p-value we should be using. And what David was talking about was, okay, let's augment a p-value with a posterior probability. So understand what's the probability that we're looking at a positive effect. Both of those perspectives were answering a very important question, but one that's a dichotomous answer, which is there an effect, yes or no? And I think as we all look towards building a risk identification system, of course we'd like to be able to say what are the effects of medical products and to be able to declare them and list them out. What I want to do is take you through a quick journey to talk about a slightly different question, which is what is the probability that that observed confidence interval that we estimate contains the true effect size? Or in other words, if I were to simplify it, instead of just asking is there an effect, yes or no, I want to answer the question, how big is the effect? And what can we learn from observational data that actually tells us about that effect size? So the paper that we've been discussing throughout, clopidogrel and GI bleeding, what we saw and what we've been showing repeatedly is that published paper gave us a relative risk and a confidence interval. That relative risk was 2.07. That confidence interval was 1.66 to 2.58, and by conventional statistics, there's a traditional interpretation of that. That is, the 95% confidence interval, it contains the true effect size 95% of the time. And that is, if we were to do 100 experiments like that, we would expect the true answer to be contained somewhere between 1.7 and 2.6, 95% of the time. And based on an unbiased estimator and standard statistics, we should expect that to happen. Now, what the consequence of that is, when we see those numbers, the way that we typically kind of interpret that is we say relative risk of 2, I guess that means it's a doubling of the risk. And confidence interval from 1.7 to 2.6, I guess the effect size is somewhere between 70% increase and a 160% increase for clopidogrel association with GI bleed. So in theory, if we were dealing with unbiased estimators and we had a perfectly calibrated model, if we were conducting large randomized clinical trials, we could probably get away with that interpretation that 95% confidence interval contains the true effect size 95% of the time. The question that we were able to use the OMOP experiment results for is, in practice, when we conduct observational studies and we apply these different standardized analytics to our suite of databases, how often is it actually the case that the 95% confidence interval that an observational study would report out actually contains the true answer. And so what I'm going to walk you through is both what we observed in our experiment and some empiric calibration tools that we've developed to hopefully overcome some of the limitations that we've observed. So just to give you a spoiler alert, I know it's late in the day and people might be falling asleep. So in our experiments, 95% confidence intervals, which are supposed to contain the true effect size 95% of the time, they actually contain the true effect size less than 50% of the time. And before anybody gets too worried about it, what we can tell you is we've developed a strategy that actually helps us better calibrate confidence intervals and get us back to the nominal 95% coverage probability that we'd like to see. And it has, I think by going through this exercise, it's helped us understand and be able to better explain why we're observing the types of variability that we're seeing in our studies. So I just mentioned the word coverage probability, and let me just explain what this is. We can ask the thought experiment, what if a study design was applied across a large set of drug outcome pairs, our positives and negative controls, but we had test cases where we knew the true effect size. And this is where our OSIM2 simulation is going to come in handy, where we know we can inject relative risks of known sizes. And when we inject signals of known sizes, we can ask the question, I'm going to apply a method to a database, the method is going to spit out a confidence interval, and I can ask a very simple question, does the confidence interval contain the true injected signal size? And because we have the luxury of being able to study a very large number of test cases, it means we can now actually estimate what proportion of the time does the real answer, is it subsumed within that confidence interval. So again, if I were to do 100 test cases, what we would expect to see is that the true answer is contained inside of the 95% confidence interval 95% of the time. That would give us a coverage probability of 95%. So one of the challenges, of course, we have is in real data, we don't actually know what the true effect size is. We can make an assumption, which is for our negative controls, we assert that there is no relationship between the drug and the outcome. Because we make that assertion, we can assume that the true effect size for our negative controls is a relative risk of 1. And we can look in our real data to basically ask the question, how often is it for our negative controls that the confidence intervals contain 1? But the opportunity we now have by using simulated data is that we can inject signals of known sizes and ask the question, when we have a positive effect, a relative risk of 2, how often is it that the confidence interval contains 2? And so what I'm going to do is I'm just going to walk you through some examples of how that actually played out. Okay, so just one extra word about the coverage probability. We want to get an answer that says that the 95% confidence interval has a coverage probability of 95%. That would mean that we've got nominal operating characteristics. There's 2 reasons why we could have miscalibration, that is, the coverage probability would be off. One is bias. So the observed point estimate could be shifted away one way or the other, and you saw that from Martine's talk, that in fact some methods were just positively biased and others were negatively biased. It's also variance, the variability in the types of estimates that we observe. If the coverage probability is less than 95%, that's not so, that's a problem, because you'd like for you to have confidence. When we say it's 95% confident, we want to be 95% confident. And it could either be because the point estimate's skewed or the confidence intervals might just be too tight. It's equally a problem, though, if we have a coverage probability greater than 95%. If I got a coverage probability that covers everything, maybe you're being too conservative in how you're representing the real uncertainty that exists in the data. Okay, so let's build this up. So we're going to apply that case control study from Epidemiology et al. that was applied for clopidogrel and GI bleed, applied to the CCAE database. But what we're going to do is first look to see what happens when we apply it to the real negative controls in the real database. And so we're going to build this up from starting with zidivudine. which is a negative control. It's an HIV product, not known to be associated with GI bleed. And what you can see is actually kind of good news. So when we applied this case control design, we got an effect estimate of a relative risk of 0.9, and you can notice that confidence interval, it straddles 1, right? So the nominal value is in there. So that's good. We'll give the method credit for nailing that particular estimate. On the flip side, let's jump from Z all the way to A. We've got abacavir. Abacavir is another HIV treatment. And yet when we applied that same exact study design to abacavir, what we observed was that it generated a statistically significant effect, a relative risk of 1.2, and that lower bound was 1.03. That is, it does not contain 1. If we only had these 2 test cases, I'd be telling you that the coverage probability is 50%. 1 out of the 2 test cases contains the nominal value. But of course, the value we've got in the OMOP experiment is we have a large set of negative controls, so we can get a better estimate of the coverage probability than just these 2 test cases. So here is a plot that's actually showing all of the negative controls for GI bleed and what happens when we apply a case control design. And rather than trying to read all those drugs or look at all the dots, the cheat sheet here is green means it covers 1, orange means it misses it. And what you notice in the picture, and this is consistent with what Martijn showed you, what you notice in the picture is that, well, first of all, you'd only like to see 5% oranges, and unfortunately we got a bunch more than 5%. And it also looks like the majority of the oranges seem to be greater than 1. That is, the method has a positive bias that exhibits itself and generates statistically significant findings. Well, just to quantify this, across our 65 negative controls for GI bleed in real data, when we look at our coverage probability, what we observed is the coverage probability is only 45%. That is, that 95% coverage probability, confidence interval that's supposed to give us a 95% coverage probability is actually only containing the real value 45% of the time. And in this example, we can see both positive bias, the estimates seem to be shifted a little bit to the right, and underestimated variance. Both of those could be at play here in explaining why we're not getting what we would like. So let me shift gears. So what I just showed you here was real data using the negative controls. But of course, the challenge is we'd really like to know what's the coverage probability for positive controls. What happens when there's a real effect in the data? And so that's why we need to shift gears to the simulated data. And we're going to use the positive controls for the simulated data, but inject signals of known sizes throughout the experiment. And so here's what happens when we apply the simulated data prior to injecting any signal. So the nominal effect is actually a relative risk of 1. And what you can actually observe here is that the coverage probability, it's not 95%, it's not too bad. In simulation, that case control design, when applied for GI bleed, had an estimated coverage probability of 75%. Specifically, there was 6 of these effects that produced statistically significant relationships, even though none such is there in the simulation. So here's what happens when we inject a relative risk of 1.25. That's now the dotted line here, and now you can see again, same color scheme, green's covering the nominal value, orange is missing it. And what you can see is not only do we have only about 54% coverage, but it looks like when the method misses it, it misses it high. That is, it overestimates the effect, and that confidence interval is shifted to the right. That handout that Martijn and David talked about is going to show you an example of this picture just to help orient you to how to read these, because we're going to flip through a whole bunch of these to just basically give you a flavor for how this actually performs. So if the signal size is a 1.25, we get a coverage probability of 54%. If we inject a 1.5, we see the same pattern existing. Coverage probability slips to 46%. If we increase that signal to a 2, the coverage probability drops to 42%. If we inject a 4, coverage probability drops to 25%. And once again, you can see this consistent pattern being observed that the method generally seems to be positively biased, and it can't seem to overcome that positive bias throughout its estimate. Now, the consequence of that is that what we'd like, a nominal system would give us a 95% coverage probability no matter what the effect size was. And so what you'd like to have is no matter what signal size we injected, you'd get somewhere on this green dashed line. And in fact, what we observed and have started to measure empirically is that essentially all of the methods generate coverage probabilities less than 95%, and the bigger the signal is, the worse the methods are at producing confidence intervals that in fact contain the truth. That is, large effect sizes tend to generate confidence intervals that might be shifted one way or the other and not containing the true value. Okay, so we got a little bit of a problem here. We need these blue stars to be on the green dashed line. But first we want to try to understand, well, this was case control, and we think case control is a little bit wonky anyway. What happens with other methods applied to other outcomes? So first, just one more representation of the same exact information, and one way you could think about it is ask the question, well, how far off was case control? And what I'm showing you here is on the x-axis, I'm showing you the true relative risk, what we injected into the simulation. And on the y-axis, I'm showing you the estimated relative risks that were observed across the suite of test cases that we examined. And so just to give you an example, if I read off on a relative risk of 2, when we injected a 2, we know the answer is 2. You can see that on average, a case control design actually estimated somewhere closer to a 3, and sometimes a case control design estimated somewhere around a 1.7. Sometimes it estimated all the way up at like a 5. Well, if we look at this plot, we notice two kind of issues. What you'd like to have, a perfectly functioning method, would have the little diamonds right on the dotted line. That is, what's in the data is actually what's estimated, and you wouldn't have so much variability. That is, you wouldn't allow for tolerance of the method moving around. Instead, what we see here is the case control design is what we observed in this particular scenario is that it's positively biased. All those diamonds are above the diagonal line, and there's a fair amount of variability in the types of estimates that were observed in the data. And so basically both of those elements, how much it's shifted and how much variability exists, what we need to do is think up a solution for how we can back that out of our analyses so that we can overcome this problem with coverage probability. So, yeah. So, okay, so the other example we talked about was isoniacid and liver injury. Again, this was the new user cohort design. It's not dead yet, so we'll keep it alive for a little bit. And again, that study produced a large effect estimate. Here's what we observed when we looked at the real-world data in the Medicare population, looking at all of our negative controls for liver injury. And this is very consistent with what Martijn showed you, which was that you don't observe with the cohort method that the method's either positively or negatively biased. It's not that a cohort method always gives you a big estimate or that it always gives you a negative estimate. Instead, what we observed was remarkable variability. Across all these test cases, you know, if the answer is 1, you'd like the estimates to be pretty close to 1 and closely bunched around 1. And in fact, what we observed was even with propensity score adjustment and the new user design elements, that we saw estimates, you know, being quite low and statistically significant and quite high and statistically significant. And in this case, the coverage probability was only 50%. Switch gears and think about simulation. Prior to injecting any signal, we actually observed pretty much the exact same phenomenon in simulated data that we did in real data. That is, if on average we looked at all of those dots, they actually look more or less like they're centered on 1. So that's actually good. Maybe the method isn't fundamentally biased one way or the other, but it's really problematic that it's possible to apply this method to something where there's no effect and either get something really small or something really large. And when we inject, and when we look at that, that's giving us a 46% coverage probability. We want that to be 95%. And yet, as we inject signals, a 1.25, a 1.5, a 2, a 4. What you can see is that the coverage probability is consistently poor, and yet, more or less, those estimates, they kind of look like they're centered around the true value. The problem appears to be that each of those estimates has a confidence interval that's just much too narrow. If we could only figure out a way to stretch out those confidence intervals, then maybe they would start to cover the nominal injected value. So here again is the plot looking at the coverage probabilities for the new user cohort design when applied to acute liver injury. we see the coverage probability starts around about 50%, and it steadily declines as the effect size increases. Okay. Now here's that same plot, and you can see actually the diamonds are pretty close to the dashed line. It's not that the method in this particular outcome is fundamentally biased, it's just that we've got a really big variability problem. And again, contrast this to what we just saw with the case control design. The case control design, we had a real big bias problem. The variance problem wasn't as big. A key message, if you take away nothing else, is just as we can't have a one-size-fits-all solution for methods, we can't have a one-size-fits-all solution for interpreting effect estimates. But in fact, every method applied to every database for every outcome needs to be properly calibrated to better understand what could happen so that you can more properly interpret what did happen when you did your individual study. Okay, so unfortunately, you remember Martijn and David saying that, yeah, the published literature method didn't work so well, but we've got an optimal that seems to do better. Problem is, even when we apply our optimal method, even if we select in this context the self-controlled cohort design within observational screening, we still have the same problem. And in fact, across all the methods we tested, across all the outcomes, and across all the databases, our coverage probability was poor, less than 50%. And so this isn't an issue that we've just got one method's got a problem. This is actually a fundamental issue with how we think about calibration and what we need to do to overcome this. In particular, if you think about a confidence interval deals with the standard error. Standard error is about sampling variability. We're dealing with really big databases. Sampling variability is not our biggest problem. On the flip side, we're dealing with observational data. Bias is our problem. Bias is nowhere in the calculation of a standard error. And in fact, due to this disconnect, that standard error is a sample size issue, and our problem in observational data is a bias issue. What we've tried to do is develop a strategy that actually allows us to formally quantify the amount of bias and integrate it into our confidence interval calculation so that we can expand the confidence interval to not just deal with sample size, but to also account for the variability that we're observing here. Okay, so let me recap before I give you the solution here. So the traditional interpretation of a 95% confidence interval, it should cover the true effect 95% of the time. And yet what we observed across all methods, across all databases, across all outcomes is that the coverage probability is actually much lower. And we observed that different methods, it seems to be more or less due to bias, and some methods due to variance, where the case control design was positively biased, the cohort design seemed to have more of a variability problem, self-controlled design actually had a negative bias. And unfortunately, the bigger the effect, the lower our confidence that the coverage that the confidence interval is telling us what it's supposed to. So that's the gloom and doom part. So hopefully now everybody can pick up and be more excited, because we actually have developed something I'm really excited to share with you, which we think is actually providing an empiric strategy to overcome this observation. So I'm going back to that case control study. I told you that when we apply case control designs to the GI bleeding problem, we saw this positive bias and we saw the variability of the estimates. So here's an idea. If there's some way we could quantify exactly how off we were, maybe we could use that information to back it out of the estimate. So think of it very simply. If I told you that you wanted to estimate a relative risk, and I told you that no matter, let's say that you knew the true effect was 2, and I told you that the estimate of a method was always going to be 2.5, well, you'd say, well, if the real answer is 2 and the estimate's going to be 2.5, I guess what I should do is just subtract 0.5 out of my estimate, and that'll get me back down to where I was supposed to be. Well, in fact, we won't go through the mathematical details, but effectively what we're going to do is exactly that. We've measured how much we need to pull the effect estimate down or up, as the case may be, and we've also tried to calibrate how much we need to stretch out the confidence interval to account for the variability that we observed. And effectively, the way that actually works is we've got all of these dots, and we can actually just fit a linear line. And going back to your basic algebra, we can actually estimate the slope and the intercept of this line. And what you can observe is the difference between the line we fit and the black dotted line. That's basically how much positive bias exists. That's how much we want to back out of the estimate. And so too can we fit a linear line to the variability. That's basically how much you want to stretch out your confidence intervals. And so what I'm going to do is I'm going to walk through what happens when we apply this strategy of quantifying the bias and then integrate it into our effect estimate, and what happens to our confidence intervals. Okay. So here's where we started. I just showed this plot just a couple minutes ago, but just to orient you again, these are the case control design for GI bleed when we're simulating no effect. That is the relative risks 1. And this is where I showed you that in the original estimates, we had a 75% coverage probability because there were 6 estimates that overshot the mark. That is, they had confidence intervals greater than 1. So intuitively, the thought would be, well, if it's seeming to overshoot the mark a little bit, maybe we could back out a little bit of that estimate, or maybe we could spread out the confidence intervals so we're not missing the target 25% of the time, but instead we have 95% coverage probability. So on the right-hand side, this is our calibration. This is after we've applied our empirical model to shift the point estimate and stretch out the confidence intervals. And what you observe on the right-hand side is now those estimates that were statistically significant before, erroneously, what you see is, like, if we look at this top one, valdicoxib, it was statistically significant before, even though it shouldn't have been. And sure enough, what you see is when we account for the variability that we observed, that confidence interval got a little bit wider and now, in fact, contains the nominal value of 1. And you can see actually the majority, in fact all, of the estimates that were erroneous on the left-hand side were basically downweighted and pulled close to 1 because we've now accounted for both the bias and the variance that we observed empirically. One consequence of that was this one down here, phenoprofen. It actually covered the nominal value of 1. But unfortunately, due to our calibration, because we basically said we need to shift everything a little bit down, we just shifted that one from covering the nominal value, shifted it down, so now it's actually saying that it's preventative. Well, okay, so we got one wrong. We fixed 6 of them, but we got one wrong. Well, that gives us a coverage probability of 96%. I want to go back to a comment I made before. We don't want a coverage probability of 100%. We don't want methods that are telling us we're 100% certain that the effect estimate is contained. If we did, it means we're being too conservative in our confidence intervals. If we report out a 95% coverage probability, or 95% confidence interval, we want 95% coverage. And so I will contend that the fact that this phenoprofen actually popped outside of covering the nominal value is actually good. We need to have a couple misses. And in fact, our goal, our target for calibration should be, can we develop a method that calibrates to 95%? Now, this was kind of an easy case. We didn't inject a signal. The nominal value was 1. So again, applying the same heuristic, adjust for bias, stretch out due to variance. What is observed when we look through the signals that we did inject? Well, when we inject a 1.25, you can see that it was positively biased on the left-hand side, and yet now those confidence intervals are stretching out on the right-hand side. Our calibrated coverage probability was, again, 96%. As we increase that to 1.5, again, our coverage probability is now up at 92%. Even though on the left-hand side the coverage probability of our nominal estimates is going down, we're able to maintain the stability of our calibrated confidence interval. That is, remember that picture where I showed how the variance was wide and getting wider and wider? By having an empiric calibration, we can take that into account to adjust our estimates. Even all the way to the extreme of a relative risk of 4, where we end up, look at on the left-hand side, what the method was doing before was estimating pretty tight confidence intervals, falsely giving you this sense of confidence. What our method actually suggests you need to do is stretch out those confidence intervals quite a lot to make sure that they cover the nominal value. And in this case, we overshot the mark just a little bit. We end up with a coverage probability of 100%. Okay. So again, compare and contrast those blue stars, that's where we were before. The nominal coverage that we observed just using the effect estimates, like everything we observe in the published literature. Those red stars up top, that's what we were able to generate using our empirical calibration. So the idea is, now that we can actually measure the bias, we can measure the variance, we can now formally integrate that into our analysis to produce more reliable effect estimates that now when I say the answer is somewhere between 1.7 and 2.6, I actually mean that 95% of the time the answer is somewhere in between there. As opposed to our current observation, which is I tell you it's somewhere between 1.7 and 2.6. What I'm really telling you is, well, half the time it might be in there. The other half the time, who knows? So I just showed you the case control model, and that was the one in the top left-hand corner there, which basically said, well, case control was positively biased, and it didn't have too much variance, so that seemed to work fairly well. But as I mentioned again, and it's a key theme here, just like there's not a one-size-fits-all solution, if we look at the next plot over, for the same outcome, GI bleed, if I look at self-controlled case series, in fact, self-controlled case series tends to be negatively biased. And actually, Trevor Shaddix and Mark Suchard at UCLA are actually working to think about maybe some of the reasons why this might be happening and how we can overcome it. Until they come up with that solution, though, basically our approach is to say, well, given that the method's currently negatively biased, maybe we need to pull up the estimates, make them bigger than what the method's actually estimating, and figure out exactly how to incorporate that. In the lower left-hand corner, if I talk about liver injury, we've got that cohort method, and you notice with the cohort method, we don't really have a bias problem. That is, the estimates are more or less consistent with where they should be. We've got a variance problem. And on the right-hand side here for the self-controlled cohort design, we notice that there's not so much variance, but this looks like the larger the effects get, the more that we're underestimating the true effect. So the question is, this empiric calibration approach that we're talking about, measure the bias, measure the variance, integrate that into your analysis to shift your estimated point estimate, stretch out your confidence interval. The question is, how well does it work, not just for that case control design, but for all four of these scenarios? And what we're really excited to show you is that what we were able to observe is that, by and large, this empiric calibration approach, it actually seems to work. No matter which method, no matter which database, no matter which outcome, if we first measure empirically the bias and the variance that exists prior to calibration, we can integrate that information into our calibrated estimates, and across all databases, across all methods, across all outcomes, what we're able to observe is we are able to get coverage probabilities that are basically right around 95%. So we think this is a real big opportunity for us to have a better way to have more confidence in interpreting the estimates. So rather than getting an estimate, not knowing whether or not, typically, I'm as guilty as everybody, we write an observation, or we do an observational study, we say, oh, we found a relative risk of 2, and then we write up in the discussions a little paragraph that says, yeah, that might not quite be right, there's bias that we're not so sure about. Well, this is actually a way to formally quantify exactly why we're not so sure and to integrate that into our estimates so that we can actually account for that in the numbers that we're actually reporting out for our studies. So just to recap, traditional confidence intervals don't provide us the nominal coverage that we're expected, and it seems to vary significantly by method, by database, by outcome. However, this empirical adjustment approach that we're saying, a framework of measuring the bias, measuring the variance, integrating that into your analysis, by applying that, no matter which database, no matter which outcome, no matter which method, we were able to achieve the nominal coverage probability that we want to see. Everything I just told you is predicated on the use of simulated data, and that's a pretty big limitation. Future work, what we'd like to be able to do as a community is to think about how we can develop these heuristics so that we can not just learn from simulated data, but also apply this to real-world data as well, and we have some active research going on to investigate exactly that. All right, so I promised you one more toy, and I'm not going to disappoint. So you just heard 3 talks that were way dense, super complicated, and probably not very well delivered. So because of that, we're just going to make a web app for you to make it a little bit easier. If you guys want to pull out your droids or your iPads or your laptops, you can go back to Elmo, or you can scan a different QR code here. And what I'm going to show you here is actually an additional component of the tool that you can play with. So if you go to elmo.omop.org, what I showed you before was you could pick your database, pick your outcome, and pick your method, and you'd get your ROC curve. But in fact, what we've also provided you is the utility to pick your database, pick your outcome, pick your method, and then you just picked up the latest copy of Annals of Internal Medicine. It said that they applied an observational screening method to liver injury for Medicaid, and they achieved a relative risk of 2 and a standard error of 0.2. Oops. And what we're able to provide you, so on the basis of that, what you would traditionally read out of that journal article would say, okay, effect estimate's 2. It would report a nominal 95% confidence interval, so it'd say it's from 1.4 to 2.9. It would say p-value is less than 0.001, so it must be significant. What we're able to now provide you is the empiric calibration tools that you just heard about from Martijn and from David and myself. Specifically, you can now see if that's what the study told you, here's how you should interpret it. That calibrated confidence interval actually goes from 1.2 to 17. The calibrated p-value is 0.016. It's still significant. It actually it is beyond a value of 2 is actually beyond the empirical null distribution. And as David shows you, you can decide on your own prior distribution and read off what your posterior probability should be. So we could say, well, if I was going into that skeptical and I had a 10% prior, and now my confidence is increased only marginally. I've gone from a prior of 0.1 to a posterior of 0.2. You can see what your ROC curve was for that method that you've just selected. And once again, you can try to get a handle of how many true positives, how many false positives, and how many false negatives would be observed had that method been applied to a larger set of test cases. So what we hope is that by providing you this tool, it'll give you a sense to be able to play with what we've come up with, to be able to see not just the examples that Martijn and David and I presented, but actually what's actually in our web app is essentially all of the optimal selections, all of the literature articles that Paul went through, and you can basically play for yourself to estimate the relative risk and the standard error. What's probably most significant about this is, what we're excited about is, it's not just about the results OMOP's generated, it's about the framework that I think we're developing that as a community we should be able to apply, not just to OMOP's 5 databases and OMOP's 4 outcomes, but instead if there's a future database or a different outcome that we would like to study. If we want to build a risk identification system for some other question of interest, now we have an empiric framework for measuring what we can expect to happen and a strategy for how to apply what we expect to happen to our analysis to give us a more credible way of interpreting observational studies. So with that, I'll stop, and thank you for your attention.